In 2017, a single paper changed artificial intelligence forever with four simple words. Attention is all you need. But what does that attention actually look like inside a large language model? How does math transform static words into context-aware reasoning? In this video, we're going to break down the entire transformer architecture step by step, from vector geometry and multi-head attention all the way up through 32 stacked layers to final token prediction. So tokenization maps DeepSeek to token ID 1284. This ID queries our embedding matrix, W embedding, pulling out row 1284 as our static vector. Notice the flaw though. Whether DeepSeek is a company noun or an action verb, it gets the exact same vector every time. To see why this rigid lookup fails, let's plot this vector in 3D space. In 3D space, we have two targets, a company space and a verb space. Because our lookup table forces one fixed vector x static, it sits stuck halfway between both meanings. It gets pulled toward company for nouns and action for verbs. It's a bad middle compromise. One static vector can't be in two places at once. We need context to fix it. Before we can update vectors with context, we face a second issue. Static vectors have no sense of word order. Let's fix that next. Transformers process all tokens at once. Without positional data, word order is completely lost. Shuffling DeepSeek as a Chinese AI company destroys its meaning. To inject order, we use sine and cosine waves across different frequencies. At position 3, these waves generate a unique positional vector. We add this vector to our embedding. Now the model knows who the word is and where it sits. Now that our vector carries position, how does it talk to other words to gather context? It projects itself into three distinct roles. To gather context, one static vector must play three distinct roles. We project it through three matrices: into a query, a key, and a value. Let's see how these three roles drive scale dot product attention. Query asks what to look for. Key advertises token content. Value holds information passed along. The formula dots query and key scales down by the square root of dk, applies softmax, and weights the values. Here, matrix X represents our final input embeddings already combined with positional encoding. Geometrically, weight matrices rotate these combined vectors into three distinct subspaces. Numerically multiplying by WQ, WK, and WV generates explicit 4D vectors making dk equal to 4. Here we're computing the matrices. We dot DeepSeek's query across all keys. Company scores highest eventually at 1.18. So we go through all the columns to get to that number. Since dk is equal to 4, we scale raw scores by the square root of dk dividing by 2. Softmax gives clean weights 22% attention to company. Weighting the values yields Z DeepSeek, our token's new context-aware vector. So looking through one lens isn't enough. What if a token needs to analyze syntax, entities, and long-range dependencies all at once? Instead of relying on a single attention calculation, real transformers use multi-head attention to analyze a sentence through multiple lenses simultaneously. Head 1 evaluates entity types, linking DeepSeek to Chinese and company. Head 2 and 3 focus on grammar and syntax, watching surrounding word roles. Heads 4 and 5 track local domain context and immediate neighbor tokens. Head 6 monitors self-identity, while Head 7 captures long-range dependencies across the sequence. And Head 8 evaluates high-level semantic meaning, giving us 8 parallel representations. We take all 8 head output vectors, H1 through H8, concatenate them end to end, and project them through WO, blending all 8 perspectives back into a single vector. Now that multi-head attention has calculated this context update, how does the transformer safely integrate it into the network? Inside a transformer block, input vectors enter multi-head attention to compute context updates. A residual skip connection adds the original input back in, preserving word identity before layer normalization. A feed-forward MLP, multi-layer perceptron, processes complex features followed by a second residual add. That completes layer 1. This single block is just the first floor of a massive building. Let's zoom out to see the full macro architecture. Modern LLMs stack 32 of these complete transformer blocks vertically. Shallow context in layer 1 deepens into complex semantic reasoning by layer 32. The layer 32 vector enters the LLM head. Softmax converts the output into probabilities, predicting company at 74%. We saw the next token probability, but what actually happened to our token in geometric space across this entire pipeline? In sentence B, the exact same starting vector gets pulled into the action verb cluster by layer 32. That's the power of transformers. It turns rigid static tokens into dynamic, context-aware vectors. Thank you for watching this video, and I hope to see you soon.